It rules the solar system. It is a megaworld with a mass 2.5 times that of all other planets. This spinning giant generates dangerous radiation, violent hurricanes, and magnetic fields. The spacecraft can charge into the Jupiter maelstrom and reveal its secrets. Juno is part of a larger effort that aims to look into giant Jupiter and see a time 4 billion years ago when planets were created and destroyed, tossed into space or into the sun. This was the time when the fate of our small, agile world was in balance. He was also known as Zeus by the Greeks and Jupiter by the Romans. His evil deeds were hidden behind swirling clouds by the king of gods. His wife Juno, the goddess Juno, could see through the misty clouds to catch him. Juno, NASA's Jupiter near-polar orbiter sent by NASA, left Earth to study the Jovian atmosphere, to discover clues about the powerful forces at work beneath its cloud tops. Jupiter is home to over 70% of the total solar system mass. Its mass is 300,000 times that of Earth. Juno is the latest mission in a series designed to measure the planet's properties, its growth, and the shaping of a rocky blue globe worth. As the supreme deity in ancient pantheons, Zeus or Jupiter was revered and feared for his immense power and influence. Yet, his mythological stories also reveal a god that often engaged in morally questionable acts. Similarly, the planet Jupiter possesses an unparalleled gravitational influence on the solar system, which has shaped its formation and evolution over time. Launched in 2011, Juno's mission aimed to unlock the secrets of Jupiter, from its powerful magnetosphere to its turbulent atmosphere. The spacecraft was equipped with advanced scientific instruments to probe the planet's internal structure, magnetic fields, and chemical composition. By unraveling Jupiter's mysteries, scientists hope to gain insights into the formation of our solar system and the conditions that led to Earth's development. Juno's journey to Jupiter was marked by a series of groundbreaking discoveries. The spacecraft revealed that Jupiter's powerful magnetic field is generated by the planet's rapid rotation and its metallic hydrogen-rich core. These findings provided valuable insights into the dynamics of magnetic fields and other gas giants as well. Additionally, Juno's observations of Jupiter's atmosphere uncovered massive, swirling storms that extend deep into the planet's interior. These storms, known as the Great Red Spot and other smaller oval storms, have captivated astronomers for centuries. Juno's detailed measurements allowed scientists to better understand the processes driving these meteorological phenomena and their implications for planetary climate systems. The data collected by Juno not only shed light on Jupiter's unique characteristics, but also helped to refine our understanding of planetary formation and evolution. By studying the gas giant, scientists were able to draw parallels between its composition and that of the early solar system. This information was crucial in piecing together the complex history of our cosmic neighborhood and the factors that contributed to the formation of the Earth and other terrestrial planets. In conclusion, Juno's mission to Jupiter has been an invaluable source of knowledge about the gas giant and its role in the solar system's history. The spacecraft's findings have revolutionized our understanding of Jupiter and provided a wealth of information about the processes that shape the Earth and the other planets in our cosmic backyard. Astronomers have been studying the formation of another solar system to help understand Jupiter's early years. In the constellation Pictor, Beta Pictoris is growing its first crop. One of the planets is large enough to be photographed and far enough away from the star. Astronomers now know that Beta Pictoris b can be seen on both its orbits. Beta Pic will show you a snapshot of our solar system 4 billion years ago. The outer zone is where the observed planet is currently growing. There are only clouds of dust, gas, ice, and other small objects called planetesimals. The planet is likely to be a raging torrent of magnetic and gravitational energy, with matter swirling around it. Jupiter's distant cousin is also surrounded by a maelstrom that is invisible but raging. The magnetic field of the king planet is more powerful than Earth's by 20,000 times. If you look up from Earth, Jupiter's magnetic field would appear larger than the full moon if it could be seen in the night sky. Jupiter's magnetic field is so strong that it appears to extend beyond Saturn's orbit. It looks like a Zeus lightning bolt. Jupiter's magnetic field is created by a powerful double dynamo. One is deep below the planet and penetrates it, while the other is closer to the surface and rings the equator. Jupiter's moon Io moves through the magnetic field and emits strong bursts of radio energy that can be detected on Earth. Io's volcanic eruptions release a torrent of charged particles into the field. These particles in turn ignite massive auroras, which light up the poles of this huge world. The radiation belt is formed by a haze of charged particles that swirl around the planet, creating radiation 1,000 times more deadly than the human lethal dose. Pioneer, a 1973 piloted aircraft, was within 130,000 Kelvin of Jupiter's cloud tops when it flew by. Pioneer 11 captured the first close-ups in 1973 of the Great Red Spot, Jupiter's signature storm. These Pioneer observations influenced the design of twin Voyager spacecraft. Engineers shielded vital Voyager components from radiation when the spacecraft was launched in 1977. This allowed the Voyager craft to capture 19,000 images, including new views of Jupiter's ghostly rings. Its icy terrain on the big moons Europa, Ganymede, and its inner moon Io is stunning. There are also powerful active volcanoes there. In 1995, the Galilean Mission got even closer. Galileo returned a treasure trove full of information about Jupiter's atmosphere. Jupiter, whose composition is almost identical to that of the Sun, offers insight into the creation of the solar system 5 billion years ago. Stars and planets form when clouds of dust and gas contract. This is often accelerated by the explosion of nearby stars. The shockwave created by the dying star causes the clouds collapse and spin. The temperature rise is high enough to make a dim protostar as matter flows into the center. The disk is home to billions of dust particles that collide, stick together, and form chondrules. The chondrules are attracted to each other by gravity and static electricity to create pebbles. Pebbles are transformed into boulders. Finally, there are planetesimals. These objects, which can be kilometer-sized, can collide and either stick together or separate. The matter continues to float toward the central star. As the star becomes brighter, the winds of radiation blur the stars, pushing out the rest of the gas and dust. The ice line is a distance from the star. Here, the temperatures are low enough to allow water, methane, and ammonia to form solid crystals. Protoplanets are formed quickly when objects made from rock and ice combine. This is how the largest planets grow fastest. Juno's electronic circuits were protected from the harsh radiation of Jupiter by a titanium vault. The components of Juno were made from radiation-hardened materials. All parts of Juno can be wrapped in lead foil. Juno was launched on August 5, 2011. This was the second launch of NASA's New Frontiers program. The series of medium-sized missions aims to increase our knowledge about planetary bodies and provide new insight into the origins of the solar system. New Horizons was the first mission. It traveled for 9.5 years to the outer solar system. It collected data on the geology of Pluto and Charon and mapped their surfaces. This helped to uncover their complicated and violent past. OSIRIS-REx was the third mission. It was sent to 101,955 Bennu in 2016. It was intended to land on the asteroid and pick up any rocks to return them to Earth. These samples will answer fundamental questions about the birth of our solar system and the origin of organic molecules, which are key to the evolution of life. Each mission has faced difficult technical challenges to score new science. Juno's challenge was to fly near Jupiter and not get fried by the powerful radiation belts. The spacecraft was placed in a series of highly elliptical orbits that allowed it to track Jupiter's poles. It then dived beneath the radiation belts to pass within 4,100 Kelvin of Jupiter's cloud tops. Jupiter only spends 2 hours in the area of maximum danger in each 53-day orbit. The craft rotates 3 times per minute, which allows its instruments to capture approximately 400 slices of data. Juno is also taking photographs of Jupiter's complex surface features. Scientists see structures similar to Earth's atmosphere when they look at the planet. Cyclones, storms, jet streams, and anticyclones all push upward. Yet, Jupiter and its weather systems have radically different characteristics. The planet is larger for one. It rotates faster and is further from the sun's warming radiation. Its cloud tops display intricate structures that give a glimpse into the conditions deep within it. Juno's data indicates that Jupiter's surface flows can reach as far as 3,000 Kelvin below the surface. Below that level, magnetic fields slow down the planet and pull it into a uniform orbit. Scientists suspect that the inner zone may be a sphere made of metallic hydrogen and surrounding a solid core composed of rock or ice. Juno's journey into Jupiter's mysterious atmosphere has revealed remarkable findings that have reshaped our understanding of the gas giant's weather systems and internal structure. The spacecraft's ability to capture vast amounts of data from Jupiter's cloud tops has allowed scientists to delve deeper into the planet's dynamic atmosphere, uncovering the unique properties that differentiate it from Earth. Jupiter's rapid rotation and sheer size contribute to its extreme weather patterns and atmospheric phenomena. The gas giant completes a rotation in just under 10 hours, creating a turbulent environment with powerful jet streams and immense cyclonic storms. This chaotic atmosphere is further fueled by the planet's distance from the Sun, which results in cooler temperatures and complex chemical compositions. Juno's high-resolution images and data have provided unprecedented insight into the depths of Jupiter's atmosphere. The spacecraft has detected surface flows extending down to 3,000 Kelvin below the cloud tops, which is a testament to the planet's immense scale and the influence of its magnetic fields. These fields play a crucial role in regulating the gas giant's internal dynamics, eventually causing the planet's rotation to synchronize at deeper levels. The data gathered by Juno also supports the hypothesis that Jupiter's interior houses a layer of metallic hydrogen surrounding a solid core, possibly composed of rock or ice. This metallic hydrogen layer, formed under immense pressure, contributes to the generation of the planet's powerful magnetic field. The presence of a solid core, if confirmed, would have significant implications for our understanding of gas giant formation and evolution. In summary, Juno's mission has vastly expanded our knowledge of Jupiter's intricate atmospheric processes and internal structure. The spacecraft's data has offered a unique perspective on the gas giant's weather systems, revealing the factors that contribute to its extreme and turbulent environment. Moreover, the insights gained from Juno's observations have helped to refine our understanding of the gas giant's composition and the processes that drive its dynamic atmosphere. Scientists believe that Jupiter, a giant planet, formed in long orbits around their stars during the 20th century. These planets can grow by absorbing a rich supply of icy planetesimals. The ice line keeps planets small as there is less solid material in their formative years. Recent exoplanet discoveries have changed this understanding. Along with ground-based systems for planet hunting, the Kepler space missions have discovered more than 2,000 stars that are home to orbiting worlds. None of them have yet to resemble the solar system. Many star systems' inner orbits are graced by so-called hot Jupiters, large gas giants about the size of Jupiter that whip around their parent star at close range. Some of these gas giants are being stripped by powerful solar winds. A class of super rocky Earth is also available. They have twice the mass of our planet and are located in the innermost orbits of many other solar systems. It turns out, the most common planets found in these inner regions don't have any rocky surfaces. It is a class that contains gas dwarfs smaller than Neptune, which can weigh as much as 10 Earth masses. Rare, smaller planets of Earth-sized dimensions are actually possible. How did the solar system develop in such a different direction from its original design? Jupiter's turbulent history may hold the key to its past. Juno moves in close proximity to Jupiter, and its path is affected by the concentrations of mass below the surface. Because Jupiter isn't a solid planet, these regions can move and shift freely. Jupiter spins faster than any other planet in the solar system. It turns once every 9 hours and 55 minutes. This bulge is the equatorial region, and it flattens its poles. Researchers can identify concentrations of mass beneath the surface by plotting small variations in Juno's orbital timing. It is possible to determine what Jupiter is made up of, its density, its spin force, and its core mass. These are clues to the time and method of its formation. Its remnants are still present in the solar system. They are still the same wandering rocks they were when they were formed nearly 5 billion years ago. They are all so small that they burn in the atmosphere upon contact with Earth. Only a few of the larger ones survive the fall. These planetary shards were dated by scientists using molecular variations or isotopes of two specific metals, tungsten and molybdenum. These meteorites seem to be from two distinct populations that formed in different regions of the solar system. Something must have caused a wedge to separate these two regions and prevented them from mixing. The young Jupiter must have grown quickly if this great divider was to have prevented them from mixing. It reached about 20 times Earth's weight within the first few million years of the Sun's formation. Saturn, Uranus, Neptune, and Uranus were their gas giant neighbors. Jupiter could have divided the solar system this way. It would have stopped the flow of matter into the inner system and slowed the formation of large rocky planets and super-Earths. It was then that one of the most significant events in the history of our solar system's history occurred, set in motion through Jupiter's phenomenal rise. A whole new set of questions has been posed by the discovery of large gas-rich planets in the inner regions of other solar systems. Could Jupiter have followed a similar route if these huge planets were formed above the ice line? Scientists used supercomputers to simulate the early evolution of the solar system. A set of initial conditions was created to simulate the interaction between gas, dust, gravity, and electricity. We are taken to a cold, dusty corner in the galaxy 5 billion years ago. The cloud collapsed into a dense central region after shock waves from a supernova blast. A huge rotating hurricane of water, dust, and gas is located near its center. Matter flows through its eye into a star that is just beginning to form, along with a thin disk. The deceased flashes of light indicate collisions between larger objects. Their orbits are shown by the concentration rings. Jupiter, the first fully sized planet, is visible in the large orbit at the periphery. It has accumulated huge quantities of hydrogen gas and ice from its faraway position. Jupiter's response to gravity and the mass in the inner solar system within 1 million years of its creation is remarkable. This model depicts Jupiter's inward spiral, known as the Grand Tack. The inner solar system is thrown into chaos as the planet-sized giant shrinks its orbit. Jupiter throws large objects into looping orbits around outer solar systems while streaming into it. Jupiter finally feels the pull from another planet, Saturn. Then, it retreats to the outside solar system. Jupiter slowly settled into its current position. There were about 20 to 30 small planetary embryos left to monitor the inner solar system. The simulation now covers 50 million years. Their orbits become unstable as the embryos tug at one another. The number of planets will drop to 5 when the dust settles, possibly 100 million years later. This includes Earth and Theia, a world Mars size. Everything changed when Earth met Theia. The first 24 hours are shown in a computer model. Theia is only a third of the distance from Earth. The shock wave of superheated, vaporized rock that surrounds Earth's remains from the shattered wreckage envelops Earth. Earth is subject to secondary impacts as a molten ring forms around it. This orbiting ring will eventually cool down and coalesce into one orbiting body in just a century. The Moon. Earth would have been spinning on its axis if it had not been for the violent formation of the Moon. The die lasted just 5 hours. The Moon stabilized the tilt of the planet, keeping it steady over time. It slowly slowed down our planet's spin as it moved away from Earth to the current distance. The Grand Tack theory may help scientists understand the evolution of our inner solar system. For example, why is Mars so small? Jupiter may have swept up most of the dust that had accumulated near the ice line and starved Mars. How can we explain the differences between different classes of asteroids? At first glance, the asteroid Bennu appears to be a fossil dating back to the time Jupiter was sailing toward the Sun. This dark object is composed of carbon-rich clay materials that were formed in the explosions of dying stars. Bennu is itself a result of collisions. The asteroid likely has been pulled apart, stretched, and reformed over its 4 billion-year journey. Scientists have launched the OSIRIS-REx mission to track the origins of the asteroid. The mission aims to return a sample back to Earth's labs. The scientists plan to send Lucy, a second mission to the group of asteroids following Jupiter. These so-called Trojan asteroids get their name from the soldiers who hid in the giant horse in Homer's Iliad. Jupiter is believed to have started pulling them along in the first 1 million years of Jupiter's history. There's also the main asteroid belt between Jupiter and Mars, a vast hoop made up of rocks. Scientists believe that Jupiter's Grand Tack movement toward the Sun caused it to disperse a ring of rock and dust. Jupiter returned out and drew in a new set of rocks. Scientists hope to prove their origin by studying the composition of these asteroids. The giant planet also has its own artifacts dating back to the early solar system. The majority of the planet's 79 moons are comets or asteroids that were captured over time when they flew too close. These 4 largest satellites are quite different. We would call the 4 largest satellites dwarf planets if Io, Europa, Ganymede, or Callisto orbited Jupiter. Scientists believe that these moons formed slowly from a disk of ice debris that orbited Jupiter late in its formation. All 4 are in tidal lock. Each of them keeps the same orientation toward Jupiter, just like our moon. Io, the volcanic moon, orbits closer to Jupiter. Io is a reminder of the dangers that can arise from being too close to an unresponsive god. Io is continually being turned inside out, heaved and stretched through gravitational interactions and Jupiter's gravitational pull. Io has hundreds of volcanoes that spew lava up to 400 Kelvin high, making it the most active solar system body. Europa is next with its young, shiny, ice-covered surface. Ganymede is the largest moon in our solar system, measuring 5,268 Kelvin in diameter. It is even larger than Mercury, the planet. Then, there's Callisto, 2 million kilometers away from Jupiter. These three icy moons, Callisto, Europa, and Ganymede, have different amounts of water under their surface, according to spacecraft sensors. Jupiter's early years saw ice, gas, and dust flow along a circular path into the planet. According to the Grand TAC model, Jupiter's disk would have shrunk as it moved toward the Sun. It is likely that the two larger ice moons formed before this. Europa was formed later, and it had less water to attract. Io had nearly none. Jupiter's major moons didn't keep all of the planet's icy bounty. Jupiter's inward journey would have left behind a trail of ice, delivering water that could one day fill the oceans of Earth. Jupiter and Saturn began to throw more icy material into the inner solar system once they had settled down in the outer solar system. Rock and ice fell on Mars, Earth, Venus, Mercury, and Venus. This period is evident in the lunar landscape. The late heavy bombardment is a 300-million-year-old fusillade. Scientists have calculated that the planet could have been struck by at least 4 objects, each capable of turning Earth to molten lava. This is based on data taken from the Moon. Impact erosion is a process that may have been crucial to the birth of life. Hot radioactive metals such as uranium, potassium, and other radioactive elements were blasted off the planet by the impacts. This allowed the outer crust of the planet to quickly cool, allowing water to remain. Scientists believe Earth was a water-rich planet in its early years. The Juno spacecraft travels at around 200,000 Kelvin per hour and takes approximately 2 hours to go from one pole to the next. It records many readings of the world, which is still a vast work in progress. At speeds of up to 650 kilometers per hour, wind whips cold clouds of methane and hydrogen sulfide through the air, creating endless swirling artifacts. Sometimes, white clouds of ammonia powder fly above the broad southern red band and seem to disappear from Earth's view. It is cold in the clouds at -125 degrees Celsius. Showers of compressed carbon could form deep within the atmosphere between layers, creating a diamond rain. The crests of huge waves that rise and fall along the surface are marked by white spots. Propelled by heat hundreds of kilometers below, tumbling storms explode into the upper atmosphere. They unleash lightning bolts that are stronger and more powerful than any other seen on Earth. Juno has captured the polar regions for the first time. They have defied all expectations. The belts and zones at the middle latitudes are gone, and the atmosphere is filled with a multitude of hurricanes. Juno's infrared imaging device captured the structures in 3 dimensions during its 4th orbit of Earth. A giant cyclone surrounds the northern pole, with 8 smaller ones that measure over 4,000 Kelvin in width. Bright yellow colors indicate deeper, warmer regions. Cooler cloud tops are those with darker red hues. These light-colored clouds are created by the interaction between smooth horizontal flows, low latitudes, and turbulence at poles. They drift towards the poles due to the spin of their planet. The southern cyclone, on the other hand, is surrounded by 5 cyclones. Even these smaller ones look huge from Earth's perspective. They can reach up to 7,000 Kelvin in diameter, or roughly the same width as Mars. It is unknown why these structures do not merge. 4040, the Great Red Spot, is the most powerful feature of Jupiter, and it has kept us under its spell. Juno flew directly above it at an altitude of over 9,000 kilometers. It is close enough to be able to see the fine details. The history of this high-pressure zone shows that it is at least 350 years old. It has been measured by astronomers since 1830. It measures approximately 16,500 Kelvin across and is 10 times bigger than Earth's largest typhoon. Juno's data indicates that the Great Red Spot heats Earth's upper atmosphere. Every 6 Earth days, The big cyclone turns counterclockwise. As the storm gets more severe, this period is becoming shorter. Sometimes the color fades over years and then intensifies. It is not known why. Galilei was attracted to Jupiter is a bright light in January 1610. His tiny telescope was powerful enough for him to see the 4 large moons that circle the great orb. He thought that satellites could be possible on another planet, and Earth could therefore be considered a satellite of the Sun. We could only go back in time and show Galilei close-ups of Jupiter taken by Juno. Imagine how amazed he would be to discover that these giant planets are common throughout solar systems across the galaxy. It invaded our solar system billions of years back. It destroyed worlds and set the stage for new ones. He would have thought of the news that Jupiter had left behind a quiet area. A world with oceans would be able to form and, over time, give birth to live.